Welcome to an exploration of how tiny capsules behave completely differently from their larger counterparts due to surface effects at the nanoscale. At the nanoscale, shells and capsules exhibit surprising mechanical behaviors that classical theories cannot predict. The key lies in understanding surface effects. Let's start by understanding what these tiny structures actually are and why they matter. Nano and microcapsules are essentially hollow spheres with very thin walls, used extensively in drug delivery, cosmetics, and material science. A typical capsule has a thin shell surrounding a liquid or gas core. The shell thickness might be only nanometers, while the diameter could be micrometers. These structures range from 100 nanometers to 10 micrometers in diameter, with shell thicknesses often just a few nanometers. Before diving into nanoscale effects, let's review what classical continuum mechanics predicts for shell behavior. Classical shell theory gives us the critical buckling stress as a function of Young's modulus E, shell thickness T, radius R, and Poisson's ratio nu. Here, E is the Young's modulus, representing how stiff the material is. T is the shell thickness, and R is the shell radius. The key prediction is that thinner shells should buckle at lower stresses, scaling with thickness over radius. This graph shows the classical prediction. As radius increases, the critical buckling stress decreases inversely with radius. At the nanoscale, a new player enters the game, surface stress, which completely changes the mechanical behavior. What exactly is surface stress? It's the excess energy per unit area at a material's surface. Surface stress gamma is defined as the derivative of free energy F with respect to surface area A. Surface atoms have fewer neighbors than bulk atoms, creating an imbalance that leads to inward tension, like a stretched membrane. For typical metals, surface stress ranges from 1 to 2 joules per square meter. Let's understand why surface effects become dominant as we shrink down to nanoscale dimensions. The critical question is, when do surface effects start to dominate over bulk material properties? The ratio of surface to bulk contributions scales as gamma times R divided by E times T squared. As the radius R decreases or the thickness T decreases, surface effects become increasingly important. As we scale down from 100 nanometers to 50 nanometers to 30 nanometers, the surface area to volume ratio increases dramatically. Now let's see how we modify the classical shell equation to account for surface stress. The modified critical stress equation adds a surface stress term, gamma over T, to the classical expression. The first term is the classical bulk contribution we saw earlier. The second term is the surface stress contribution, which dramatically increases as shell thickness decreases. This additional term explains why nanoshells can be surprisingly stronger than classical theory predicts. Let's work through a concrete numerical example using a gold nanoshell to see these effects in action. Consider a gold nanoshell with radius 50 nanometers and thickness 5 nanometers. Gold has a Young's modulus of 80 gigapascals and surface stress of 1.5 joules per square meter. The classical prediction gives us a critical stress of approximately 4.7 gigapascals. The surface contribution adds another 0.3 gigapascals. The total critical stress becomes 5 gigapascals, about 6% higher than classical theory predicts. If we reduce the thickness to just 2 nanometers, the surface contribution jumps to 0.75 gigapascals, a 16% increase. Let's use an intuitive analogy to understand why small shells behave so differently from large ones. Think of squeezing a large ping-pong ball versus a tiny one. You apply the same pressure, but they respond very differently. For the large ball, the bulk material properties of the plastic dominate its mechanical response. For the tiny ball, surface tension becomes a significant additional factor that stiffens the structure. The small ball might either collapse at unexpected pressures or resist deformation more than you'd predict from scaling laws alone. Now let's examine how buckling instability manifests differently at the nanoscale. An important question: can surface stress actually cause instability rather than always providing stability? The answer is yes. Depending on whether surface stress is tensile or compressive and how it's distributed, it can destabilize structures. Buckling creates a wavy deformation pattern. At nanoscale, surface energy changes during buckling can either resist or promote this deformation. The change in surface energy equals surface stress gamma times the change in surface area. Buckling typically increases surface area, which raises the energy barrier and can stabilize the shell. However, if surface stress is inhomogeneous or has specific orientations, it can actually lower the buckling barrier. Nanopores in shell walls introduce additional complexity to the mechanical behavior. Porous shells have small holes distributed throughout. These nanopores drastically alter mechanical properties. When pore diameter d is comparable to shell thickness t, we see very strong effects on mechanical properties. The effective modulus decreases with porosity phi according to a power law, where phi critical is the percolation threshold. Surface stress at pore edges creates stress concentrations that can initiate failure at lower loads. A typical porosity of 10 to 30% can reduce shell strength by 40 to 70%. Shell curvature itself modifies surface stress through the Laplace pressure effect. The Laplace pressure equation shows that pressure difference equals surface tension times the sum of inverse principal radii. For a sphere, both principal radii are equal to the sphere radius r. This simplifies to delta P equals 2 gamma over r for a spherical shell. Smaller radius means higher internal pressure purely from surface stress effects. This graph shows how Laplace pressure increases dramatically as radius decreases below 100 nanometers. For a 20 nanometer radius shell with gamma of 1.5, we get about 150 megapascals of pressure. At nano-scale, multiple competing effects determine whether shells are stronger or weaker than predicted. Strengthening factors include surface stress and beneficial prestress, while weakening factors include defects and porosity. The net effect depends on the specific material, size scale, degree of porosity, and defect concentration. An important practical question: which effect dominates for typical drug delivery capsules? For sizes above 50 nanometers, strengthening from surface stress usually dominates, making capsules more robust than expected. Temperature introduces another layer of complexity to nanoshell mechanics. Surface stress decreases linearly with temperature, approaching zero at the critical temperature Tc. As temperature increases, surface stress magnitude decreases, reducing its mechanical contribution. This graph shows the linear decrease of surface stress with temperature for a typical metal. Between room temperature and body temperature, surface stress changes by roughly 10%. Dynamic loading at nanoscale introduces viscoelastic effects and frequency-dependent behavior. At high loading frequencies, surface effects become even more pronounced because bulk relaxation is slower. The critical frequency equals Young's modulus divided by viscosity eta. For soft polymer shells, the critical frequency is typically around 1 MHz. Above this frequency, the shell behaves more elastically with an enhanced surface stress contribution. How do we actually measure these nanoscale mechanical properties experimentally? Atomic force microscopy allows us to indent individual nanocapsules and measure force displacement curves with nanonewton resolution. AFM can measure forces down to nanonewtons and displacements to sub-nanometer precision. Optical tweezers use focused laser beams to trap and compress microcapsules while measuring deformation. Micropipette aspiration sucks capsules into tiny pipettes to measure shell elasticity and critical pressures. Understanding nanoshell mechanics is crucial for medical applications like targeted drug delivery. Drug delivery capsules must be strong enough to survive the bloodstream, but weak enough to release drugs at the target site. The capsule travels intact through the bloodstream, then releases its drug payload when triggered at the disease site. Engineers tune surface properties to control circulation time and design the release mechanism. Let's directly compare how mechanical properties scale from macro to nanoscale. A 1 mm shell is dominated by bulk properties, while a 100 nanometer shell has significant surface contributions. The ratio of nano to macro critical stress equals 1 plus a term with gamma times macro radius over E times T squared. Going from 1 mm to 100 nanometers represents a size reduction factor of 10,000. The surface contribution scales inversely with thickness squared, becoming huge for thin nanoshells. Real nanocapsules often deviate from perfect spheres adding geometric complexity. Ellipsoidal shells have two different principal curvatures, creating non-uniform stress distributions. The maximum stress equals average stress times a factor depending on the aspect ratio of semiaxes A and B. Regions of higher curvature experience stronger surface stress effects, creating weak points. Buckling often initiates at these high curvature regions, where stress is concentrated. Many advanced nanocapsules use multilayer shells to optimize mechanical and functional properties. A multilayer shell has distinct layers with different materials and properties, each with its own surface stress. Each interface between layers contributes its own surface stress, with signs depending on material compatibility. The total stress contribution is the sum over all layers of gamma I divided by thickness Ti. Engineers can create beneficial compression or tension by carefully choosing layer materials and thicknesses. There's one key dimensionless parameter that determines when nanoscale effects dominate. This parameter lambda equals surface stress gamma divided by Young's modulus times thickness. When lambda is much less than 1, we see classical bulk-dominated behavior. When lambda is between 0.1 and 1, we're in a transition regime where both effects matter. When lambda exceeds 1, surface effects completely dominate the mechanical response. This graph illustrates how total stress changes with the dimensionless surface stress parameter lambda.